This is an in-class activity for chapter 12. Let's do the example of a coefficient of restitution. So here's the thing, here's the problem. We have basketballs dropped from a height of 2 meters onto a gymnasium floor. If the coefficient of restitution between the ball and the floor is 0.9, how high will it bounce? What we do is that we say, well, E equals the square root of h bounce over hd, and then h bounce we don't know, h drop is 2, sorry, and that is 0.9. First of all, you square it, so this is 0.9 square, and that's going to be equal hb over 2. Then you do cross multiplication and you'll get hb on its own. So if you look at the solution here, that's hb over 2, you square 9 by 9 is 81, but you have 2 decimal points positions, that's 0.81 equal hb over 2. Do cross multiplication, hb will be 1.6 meters. And that's 3 significant figures, so it should be 1.62 meters. That's our hb. Next problem, it's work and energy example. So let's say we have a person, 580 Newton person, runs up a flight of 30 stairs of rise. Each one of the stairs is 25 centimeters in 15 seconds. How much mechanical work? Remember, when we said mechanical work, it's force multiplied by displacement. It's not a distance. So displacement is going from initial to final, correct? So how would you do that? If you want to do this, you will say that the work equals force multiplied by distance. Now the force, the only force that is acting is the weight. It's 580. Now you need to multiply it by the distance. Remember, it's not this pathway. It's the difference between initial and final. That's displacement. So all what I want to do is multiply 30 by 25 centimeters. So you do the 30 multiplied by 0.25. 4.35. Now it's kJ. Work is Newton meters, which is joules. Now what about power? So power is W over time, right? 4.35 K divided by how many seconds? 15. You get your power. And power is in which unit? Watt, right? W. So you will end up with this value, these values. So we did the force multiplied by the distance, which is actually the displacement. It's not the displacement. And then the power, you divide the work by the time, and then you give you the watts. And that's 290 watts. Now, for another energy example now here. So let's say we have a 2 kilogram ball is dropped from a height of 1.5 meters. What is the velocity immediately before impact with the floor? This is a potential energy, kinetic energy problem. Remember, it should be conserved. The only force that's acting on this object is just the gravity, correct? So I will say that, well, conservation of energy, say that C equals kinetic energy plus potential energy. Now, when the ball is on the top here, do I have any kinetic energy? It's just dropping, right? So that's 0. So that's equal to 0 plus potential energy is mgh, right? So what is my mass? It's 2. The gravitational force, 9.81. The acceleration, sorry. Gravitational acceleration. And the height is how much? 1.5. So that's your, summation of energies. So that equals 29.4 joules. Yeah, that's 3 significant figures. So this is my summation of kinetic energy and potential energy. So this value here should be the same value down there. The difference is that down there, we don't have potential energy because the distance before hitting the ground should be 0, right? So I don't have h, I don't have height. So the potential C here should equal to kinetic energy plus potential energy. I don't have potential energy. So C here is equal 29.4 equals kinetic energy half mv square. M is 2 kilograms. So you take this, you substitute this here 2. I have one equation with one unknown, right? That we can find V. So if you do this here and you do the calculations, potential energy plus kinetic energy at the top, we don't have kinetic energy, it's just potential energy mgh. We got that. Now at the bottom, when it dropped down here, I don't have potential energy because the distance is 0. That is gone. You just have this C here, do the substitution, you will get V square, take the square root, and then the velocity immediately before hitting the ground is 5.42 meters per second. Another example about the work energy. So let's say how much mechanical work is required to catch a 1.3 kilogram ball traveling at a velocity of 40 meters per second. So we're going to be using the conservation of work. The relationship between work and energy. The work is the change in energy. Because the ball is moving in a straight line, do we have any changes in your potential energy? Is the height changing? No, same height. So if you say W equals the difference in change in potential energy plus the change in kinetic energy plus the change in thermal energy. Now, thermal energy, we will neglect that because we don't have anything that is going to produce that much energy. Potential energy, we're going to neglect it because it's the same height. So there's no change. It will be the same potential energy. The change will be 0. So that's 0, and that's 0. Now the change in kinetic energy, you will say that half mv square, m1 square, minus half mv2 square. So v2 minus v1. It's v2 minus v1 square, right? So that's mechanical work. So this is what we would like to calculate, right? The work. Now here's what's going to happen. Velocity 2, when the player is holding the ball, what's going to be its velocity? 0, right? Always, because he's stopping it. And that's the question. How much mechanical is required to catch the ball and stop it? So you will say that velocity is 0, so that's 0, minus half how much is the mass? Is 1.3 kilograms, right? And you multiply it by the velocity square, which is 40 square, right? So that's 40 square. And that's how much mechanical work you actually need to stop that ball. And that's one of the things that actually, I don't know if they're measuring that or they look at it, but that's an important aspect in designing the glove. So if you do this calculations, that's 0, that's your velocity, half mv square, it's 1040, but you need to write it as 1.04 kilojoules. So the work is in the opposite direction of the velocity. I added this, a description of all the formulas and what they are. You can bring this to your final exam alongside the one cheat sheet. No, that's why I wanted to give it to you, so that you don't have to add those. This way we have completed everything related to chapter 12, which is the kinetics.